We should be live by now. It should be a quick one. Still testing my own sound. Don't know why the delay. It's a bit of delay. Should it? Okay, now now we're live. It took some time to go live. That's fine. Can deal with that, considering it's quite magic what's happening. I can start streaming with press of, well, I wish I could say a button, but no, it's like more like 5 or 6 button clicks, and we start streaming. Anyway, I'll get straight into the point. Go check this website, BioniChaos.com. I'll pop the link. Well, pretty much the link should be pretty much everywhere for your convenience. So go check it out. And we have some new content for the page. Just so you know, there is a human in the loop. If you have any questions, go for it. But otherwise, just let the robots doing the job. So I have this interactive tool. I'll get the bots to review it. Bear with me. Yeah, we're using Notebook LM and Gemini. Yeah, all the models are should be pretty much the same. Not sure. Let me know what you think. Which one are you using? Which one shall we start from first? Okay, let's start from this one. See how we go.
Okay, so let's jump into this. It's a really profound challenge we're looking at. Millions of people, globally dealing with things like ALS or stroke, and they just lose the ability to communicate.
Right. The thoughts are there, the intent is clear, but the physical path for speech it's blocked or damaged.
Exactly. And that's where brain-computer interfaces, BCIs, come in, this sort of frontier tech offering, well, incredible hope, really, trying to bypass those damaged pathways.
Letting the brain talk directly, essentially. Yeah. And when we think about accessing those brain signals without surgery, non-invasively, EEG is usually the go-to starting point.
Electroencephalography.
Yeah.
The electrodes on the scalp thing.
Yeah, exactly. And the big plus for EEG is how accessible it is. It's portable, it's relatively low cost, certainly compared to invasive methods, and crucially, it has amazing temporal resolution.
Meaning it's fast.
Super fast. It catches brain activity changing millisecond by millisecond. For something like thinking or planning speeds, which happens so quickly, that's, theoretically ideal. It feels like something that could actually be usable for you, potentially.
Okay, that sounds fantastic. But there's always a but, isn't there? The catch with EEG.
Well, yeah. It's kind of a double-edged sword. While it's great at telling you when something happens,
it's not so good at where. Port spatial resolution, is that it?
Precisely. Hard to pinpoint the exact source, but maybe even more critical is the signal itself. It's incredibly faint, just this tiny electrical whisper from neurons firing.
And that whisper gets drowned out.
Completely. Buried under the brain's own background chatter. And worse, just overwhelmed by massive electrical noise from, like, blinking your eyes, clenching your jaw,
muscle
movements.
Artifacts, right? Those are way louder than the actual brain signal you want.
Orders of magnitude louder, yeah. That noise, that's the core problem. Trying to pull out a meaningful signal related to speech from that messy, low-level EEG data. that's where you need something powerful.
And that's where the AI comes in. Deep learning.
Absolutely indispensable. You need these sophisticated AI tools, like deep learning models, to basically sift through all that static and somehow find the subtle pattern that actually means something, that represents intended communication.
Okay. So the mission for this deep dive then is figuring out how AI is actually doing that.
Yeah.
How it's trying to decode speech language directly from these really noisy, complex EEG signals.
And the progress, honestly, it's pretty remarkable when you look at where things were just a few years ago. We've moved way beyond just, classifying a handful of preset words.
Which is the really goal. Right.
Right. Now AI systems are starting to generate continuous streams of text or even synthesize audio that you can actually understand as speech, all from non-invasive EEG.
Yeah, I saw some really striking examples in the research, like one system working with imagined speech, just thinking the words, synthesized Chinese words, and human listeners got it right over 91% of the time on average. It's kind of incredible.
It really is. And then there was another one for silent reading, using EEG to generate text, achieving a BLEU1 score around 40%.
Okay, explain BLEU1 quickly.
It's basically a measure of how much the generated text overlaps with the real text someone was reading. 40% might not sound perfect.
No, but going from, like, nothing to 40% accuracy on actual text from brain signals, that feels like a huge leap. It shows the AI is starting to get the structure.
It represents a really significant milestone, getting that kind of intelligibility or text quality from such noisy signals.
Yeah.
But digging into how they got those results also highlights the biggest challenge right now.
Which is the fact that these amazing results often come from really specific, constrained setups, like needing tons of data from just one person.
You hit the nail on the head, exactly. One study, great accuracy on over 500 phrases, but it needed something like 175 hours of data from one participant.
Wow.
So the massive bottleneck for actually getting this out of the lab and into the real world is, one, the lack of big, diverse data sets, and maybe even harder, dealing with intersubject variability.
Intersubject variability,
Yes.
meaning my brain is different from your brain.
Pretty much, yeah. Everyone's brain structure is slightly different. The patterns of activity for the same thought can differ. Even the skull thickness changes the signal quality. So a model trained for hours and hours on my EEG
Might totally fail on mine.
without a whole new lengthy calibration process just for you, that's the tricky part for making this practical and widespread. And it's a fascinating AI challenge, too.
And on top of that, there are still practical things like needing faster systems for real-time chat and better hardware, right?
Yeah.
Comfortable stuff you could actually wear, like dry electrodes without the goop.
Definitely. And, as we get better and better at decoding more complex stuff, intentions, thoughts, maybe even inner speech, it inevitably brings up some really big ethical questions.
Yeah, that's kind of the elephant in the room, isn't it?
Yeah.
What does it mean for, like, mental privacy if AI can start interpreting signals straight from your brain?
That's the crucial question, isn't it? The one this progress really forces us all to think about. And it's something important for you to consider as this technology moves forward. How do we balance this amazing potential benefit with the need to protect, well, what's inside our own heads?
We will make this page available for you to play with. Everything we do goes on to BioniChaos.com. Go check it out, provide your feedback.
Okay, seriously, just imagine this. What if you could understand language, like directly from the electrical hum inside someone's brain?
Uh-huh.
Not words they speak, not text they type, but the actual thought captured just from electrical signals.
It sounds like science fiction, doesn't it?
Totally. But that's the incredible frontier we're diving into today.
And it's moving surprisingly fast from fiction to fact. We've got this stack of sources, research papers, articles, notes, all exploring this edge. Specifically, how AI models are learning to pick out language from, well, the really messy signals you get from EEG, electroencephalogram.
Right. So our mission here is to kind of cut through that complexity. We want to unpack the main challenge, look at the clever ways AI is being used, maybe celebrate some breakthroughs.
Yeah, and see where it's all heading.
Exactly. Think of this as, your shortcut to getting a handle on a field that could genuinely change things. We're aiming for those aha moments for you without getting totally lost in the weeds.
Sounds good.
Yeah.
Where should we start?
Okay, so basics first. This EEG speech decoding. What exactly are we trying to do?
Fundamentally, you're using AI, right, to try and extract linguistic information, basically. What words or thoughts someone is processing directly from those electrical patterns measured on the scalp.
From the EEG?
From the EEG signals, yeah. It's really about trying to decipher the brain's electrical language.
And that sounds, well, incredibly hard because why? What's the big hurdle?
It's just so noisy. The signals are notoriously noisy. Imagine trying to hear a single whisper in the really loud, crowded room.
Okay.
Brain signals linked to language are subtle, and they get easily drowned out by all the other electrical activity, muscle twitches, eye blinks, even just electrical noise in the environment.
Okay. So that's the signal-to-noise ratio problem,
Yeah.
SNR.
That's the one, low SNR. It's the main mountain everyone's trying to climb in this field.
So everything else your body does electrically is just static, basically, making it hard to find the signal you actually want.
Precisely. It's a massive challenge. And then there's another layer. Everyone's brain is a bit different.
Right.
So an AI model trained to decode signals from me might not work very well for you without, specific adjustments, calibration.
So generalizing these models across different people is also really tricky.
A real hurdle, yeah.
Okay, so the signal's weak, it's buried in noise, and it's different for everyone. How on earth does AI even start to tackle this?
Well, that's where all the cleverness comes in. Researchers are basically using a whole toolbox of AI and machine learning methods.
Okay.
Think of them as different kinds of pattern detectors, each good at finding slightly different things in those complex electrical waves that just might, relate to language.
What kind of tools are we talking about? Are these familiar AI names?
Some might be.
Yeah.
You see deep learning models like convolutional neural networks, CNNs. People often use those for images, but here they're adapted to find spatial patterns, like across the different electrode locations on the scalp.
Okay. Patterns across the head.
Yeah. And then there are recurrent neural networks, RNNs. They're really good at handling sequences of data over time.
Which EEG data is, right. It changes moment to moment.
Exactly. So RNNs help capture that temporal dynamic.
Yeah.
But increasingly, the big player getting a lot of buzz is the transformer architecture.
Okay, transformers, like the things behind ChatGPT and all that.
The very same. Those models are incredibly powerful at understanding context and generating sequences. And it turns out that ability translates surprisingly well to decoding these complex sequential brain signals, too.
So it's not just about spotting one word, it's about the flow, maybe predicting what comes next.
You got it. And that leads into another exciting area mentioned in the sources, the integration of generative AI.
Generative AI, like GANs or those LLMs you mentioned.
Yeah, exactly. Models like generative adversarial networks and those big transformer-based language models, they're helping move the field beyond just simple classification. This signal pattern means hello, towards actually generating language output.
Whoa, okay. But how do these models even look at that raw EEG data?
Yeah.
It's just squiggly lines, right? How do they make sense of it?
No, they don't look at the raw squiggles directly. There's a critical step, or really steps, before the AI even sees the data. It's called pre-processing.
Cleaning it up?
Basically, yeah. Using sophisticated filtering techniques to try and strip out as much of that noise and artifact the eye blinks, muscle tension as possible.
Okay.
And then there's feature extraction. The AI isn't usually looking at raw voltage values. It's looking at derived features from the signal.
Features like what?
Things like the power in specific frequency bands, alpha waves, beta waves, that sort of thing. Or maybe how synchronized the activity is between different brain areas, or specific patterns that appear over time. The AI learns which combinations of these features are the most predictive of the intended word or thought.
So clean the data, find the important electrical fingerprints, and then let the AI learn the connections.
That's a great way to put it. And yeah, getting that pre-processing and feature extraction right is absolutely crucial, especially with that low signal-to-noise problem.
Okay, now here's something that seems really key in the research, maybe a bit counterintuitive. Imagined speech. What's that about?
Right. Imagine speech, sometimes called covert speech. It's basically thinking the words, forming the sentence in your head, without actually moving your mouth or vocal cords to say aloud.
Just thinking it.
Just thinking it. You activate the brain areas involved in planning speech, but you don't execute the motor commands.
And why is that so important for decoding?
Because the muscle activity involved in actually speaking creates a huge amount of electrical noise that contaminates the EEG signal. It's really strong compared to the underlying brain signal.
Ah, so by focusing on imagined speech, you get rid of a major noise source.
Exactly. You bypass the muscle artifacts, allowing the AI to focus more clearly on the neural signals related purely to the language planning itself. This is obviously super relevant for assistive communication.
Right, for people who physically can't speak, accessing their imagined speech seems like the most direct route.
Precisely. And this is where those newer AI models, especially the generative ones, are making a massive difference. They're enabling a shift beyond just identifying single words towards syncta, but towards generating continuous output.
Continuous output, what do you mean by that? Not just one word at a time?
Yeah, exactly. Instead of the AI, say, picking the most likely word from a predefined list based on the signal, some of these newer models can take the ongoing brain activity and generate a whole flowing sequence of text, or potentially even synthesize speech that corresponds to the complete thought or sentence the person is imagining.
Wow. So much more like natural language.
Much more natural, much more expressive. It's a huge leap compared to just selecting options. It gets closer to capturing the actual flow of thought.
That really does feel like a game changer. Now, we often hear about other brain interfaces too, right? Like implants. How does EEG compare?
Good question. The sources definitely touch on other BCI, brain-computer interface methods. You have invasive techniques like ECOG electrocorticography. That's where they place electrodes directly on the brain surface.
Ooh, more direct signal, I guess.
Yes, definitely. You get much cleaner, stronger signals because you're right at the source, bypassing the skull and scalp. And that often leads to higher decoding accuracy.
Ah, surgery.
But surgery, yeah. Significant risks, not something you do lightly. There are also other non-invasive methods like MEG, magnetoencephalography, or FNIS, functional near-infrared spectroscopy. They measure different things, magnetic fields or blood flow changes.
Okay, so where does EEG fit in that landscape? Why focus on it if it's so noisy?
It really comes down to practicality and accessibility. Despite the noise challenge, EEG is non-invasive, it's relatively portable, and it's much less expensive than something like a MEG machine.
So it's the one with the best shot at being widely used, maybe outside a lab someday.
That's the hope, and that's why there's so much research pouring into improving it, tackling that noise, refining the AI. It's all driven by EEG's practical advantages.
Makes sense. And all this AI development, it must need tons of data, right?
Oh, absolutely.
Yeah.
Training these complex models takes a lot of examples. Thankfully, the field is pretty good about sharing. There are publicly available EEG data sets specifically created for this kind of speech decoding research. You can find them on platforms like OpenNeuro, Kaggle, Zenodo.
So researchers can build on each other's work.
Exactly. Those shared data sets are really crucial for pushing the whole field forward.
Okay, let's zoom out a bit. The so what question. Why should this tech matter to you listening right now? What's the real impact?
I think the most immediate and honestly the most profound impact is for assistive communication.
Right.
For people who've lost the ability to speak, maybe due to ALS, stroke, severe injury, this technology offers a potential pathway back, a way to communicate their thoughts, their needs, their personality again.
Giving a voice back.
Giving a voice back, essentially. It could restore connection, autonomy. It's potentially life-changing. And BCIs, more broadly, have huge potential in healthcare and beyond.
That's incredibly powerful. But, okay, tapping directly into brain signals. That immediately brings up some big questions, right? About privacy, about what's going on inside our heads.
It absolutely does, and it should. Decoding brain activity raises really significant ethical considerations. If technology can potentially access someone's internal monologue or even unspoken intentions, how do we protect that?
Yeah.
There's a really important growing focus now on things like neurodata consent frameworks, basically designing systems where individuals have very clear understanding and control over how their brain data is accessed, how it's used, who sees it.
Neurodata consent. That sounds like a term we're all going to need to get used to.
I think so. It's part of a wider conversation about neural rights.
Right.
Yeah, the idea that maybe we need new kinds of human rights specifically focused on protecting mental privacy, cognitive liberty, as these neurotechnologies become more powerful. It's critical that we're having these ethical discussions now as the tech develops, not after the fact.
Definitely sounds crucial. So looking down the road then, what's next for this field? What improvements are on the horizon?
Well, you can expect progress on a few fronts. Hardware-wise, people are working hard on better EEG sensors, things like dry electrodes.
Dry ones, meaning no conductive gel.
Exactly. Much less messy, potentially more comfortable to wear for longer periods, easier to put on. That could make EEG headsets much more practical for use outside a lab, maybe even at home.
Okay, that's a big step for usability.
Huge. And alongside that, you'll see continued refinement of the signal processing, getting even better at filtering noise, pulling out those key features, and of course, the AI algorithms themselves will keep getting smarter. Probably more sophisticated generative models, better training techniques, all aimed at boosting accuracy and making the decoded output sound or read more naturally.
So it feels like we're still really in the early days of what this could ultimately do.
Oh, absolutely. It's a very active research area. There are roadmaps being discussed, lots of ongoing work. The challenges, especially that noise problem, are still really significant, but the progress is undeniable, and it's driven by that incredible potential for impact.
Wow. Okay. So we've gone from these faint, noisy electrical brain signals, explored how really sophisticated AI from, deep learning basics to advanced generative models is learning to pull out meaning, especially imagined speech.
Yeah, opening up these amazing possibilities for communication assistance.
Right. But we've also acknowledged those big technical hurdles that remain and touched on these really vital ethical questions about neurodata and privacy that are starting to surface.
It's a complex picture, definitely, but like you said, a hopeful one too.
It really is. And maybe it leaves you, the listener, with something like this to chew on. If we get better and better at decoding our internal imagined speech, how might that actually change our basic idea of what communication is? Does this kind of tech start to blur the line between our private thoughts and what we express externally? And if it does, what really fascinating new questions does that raise for all of us down the line?
Okay, so I'll have this page available for you to look at. Everything we do is on BioniChaos.com. Go check it out. Has some interactive tools. It will have the audio that you just heard on the page itself. And a quiz at the bottom. Test your knowledge. So what is the primary advantage of integrating transformer-based large language model into brain-to-text systems? Reduce the need of... Oops. Didn't actually press it. The enable open vocabulary text. Yep. BCI system 95% accuracy to 1-to word classification, but very low score on continuous speech to test. What does the disparity most clearly indicate? The EG hardware has poor temporal resolution. The system is effective at simple discrimination but struggles with the complexity of generative. Generative? The user was not concentrated. No, we never blame the user, do we? Reprocessing pipelines, so it's hardware. Must be this one. That's right, Sam. What is considered the single greatest impediment to developing subject-independent EEG decoding models? The lack of sufficiently powerful AI, the slow temporal resolution, the difficulty of removing power line, the lack of large, diverse, and standardized public data sets. That must be it. That's right. And that's what we're trying to do on this channel. Publish your data. Why is decoding Imagine speech considered a more difficult task for an AI than decoding over what? Why is decoding? Well, yeah, because it's trickery, because it's magic, or because it's not real. Imagine speech involves more brain regions. The neural signatures for imagined speech are generally weaker and have a lower signal-to-noise ratio, and that must be correct. In the context of current EEG research, by the way, I could issue you a BioniChaos certificate if you answer whatever 8 out of 10 questions correctly. You can put it on your resume, the certificate. In the context of the current EEG research, what is the most common application for generative models like GANs and VAEs? Visual generative models. It's about that bottleneck problem. Yeah, synthetic data. This one. Next, a tech company releases a new BCI headset for productivity, claiming its AI can infer a user's focus level. Which ethical concern is more direct? Lack of models, mental privacy, and cognitive liberty. Yay. Well, yeah, 9 out of 10. Do I get a certificate? You can get a certificate from BioniChaos. Once we deploy this on the page, it's almost deployed. And once we are deploying, we have a last audio for today. Unless you have any questions, the human in the loop can take your questions. Otherwise, go check out this website. Everything we do is available on BioniChaos.com. Go check it out and provide your feedback.
Okay, let's jump right in. You've brought us some really fascinating sources today. We're doing a deep dive into decoding speech straight from brain activity.
Yeah.
Using AI and, crucially, non-invasive EEG.
Yeah, it really does sound like something out of science fiction, doesn't it?
Yeah.
But these sources, they lay out the current reality quite clearly. You know, the science behind it, the tech involved,
Right.
how they actually process the data, the role AI is playing, and importantly, the pretty significant hurdles that are still there.
Exactly. So our mission really is to explore these sources together, trying to understand how this amazing technology actually works, see what the data says is possible right now, and be honest about what still needs figuring out.
And one thing the sources hammer home right away is the core challenge. It's less about just finding a signal from the brain and more about finding the right signal. Those specific electrical whispers linked to what someone intends to say. And they're buried deep in just a massive amount of noise.
That signal versus noise problem, it feels like the absolute foundation here, reading through this material. What does that noise actually, consist of? Why is it so incredibly hard to pull out the signal you want?
Oh, it's a huge mess, to be frank. The electrical signals we're actually after, the speech intention ones, they are incredibly faint. We're talking microvolts, just tiny, tiny fluctuations.
Wow.
And they're happening while the brain is doing a million other things that have absolutely nothing to do with speech. Just, being conscious, other thoughts, background processing.
So the brain's just constantly buzzing with activity.
Constantly. And then, layered on top of that, you've got physical movements, even something really small, like you blink your eyes, or you swallow, or maybe tense your jaw slightly.
Mm-hmm.
Those actions create electrical signals, artifacts, that are enormous compared to those tiny speech signals we want.
Right.
Plus, just electrical interference from equipment, lights, whatever's in the environment.
Okay, so it really sounds like trying to hear someone whispering across a crowded room during, like, a thunderstorm?
That's not a bad analogy. The sources use one I really like. They say the AI needs to be a masterful detective
Hmm.
to find these meaningful whispers of intention within what they call a cacophony of biological and environmental noise. Think trying to pick out one specific word whispered during a loud concert. That's kind of the scale of the challenge.
Okay, that paints a very clear picture.
Hmm.
So given that level of noise, the sources do mention there are different ways to look at brain activity, different neuroimaging tools. Why the focus on EEG here for this speech decoding task?
Well, yeah, other methods exist, like fMRI or invasive electrodes, and they have their place. But the sources really zero in on EEG for some very practical reasons. The main advantages they list boil down to accessibility and convenience.
Okay.
And crucially, it's non-invasive. You don't need brain surgery to put electrodes inside someone's skull.
Which is obviously a massive barrier removed if you're thinking about wider use.
A huge one.
Yeah.
But the sources are also upfront about EEG's downsides.
Right.
And you can immediately see how these tie straight back into that noise problem we were just talking about.
Right.
They imply, generally lower signal quality, maybe poor spatial resolution, meaning it's harder to tell exactly where in the brain the signal is coming from compared to those more invasive methods.
So it's a trade-off.
Definitely a trade-off. You get the non-invasive approach, which is great, but you potentially lose some signal clarity or precision. Makes that detective work even harder for the AI.
Okay, so you managed to capture this incredibly noisy, faint signal with an EEG cap. It sounds like, based on the sources, you can't just feed that raw jumble directly to an AI and hope for the best. There's this essential processing gauntlet.
That's exactly it. The raw EEG data, which is basically just, messy multi-channel electrical readings changing over time, is pretty useless for decoding speech intent, as is. So this multi-step processing pipeline they describe, it's absolutely critical. It's the cleanup crew, essentially transforming those raw brainwaves into something structured that the AI can actually make sense of.
So what does that pipeline involve? What are the key steps they mention?
Okay, so it starts, obviously, with the raw EEG data, that messy stuff. Then it goes into pre-processing. This is your basic cleanup stage. You're filtering out frequencies you don't want, like electrical hum. And really importantly, artifact removal.
Getting rid of the blinks and jaw clenches.
Exactly. The sources mention specific techniques like ICA, independent component analysis, which is basically a computational method to try and separate those big muscle signals from the smaller brain signals you're actually interested in.
Like digitally scrubbing out the concert noise.
That's a good way to think about it. And also segmentation, breaking up that continuous stream of EEG data into smaller chunks that might correspond to a word or a thought. Once it's cleaner, it moves to feature engineering. This is where you take the cleaned up data and transform it into a format that really highlights the patterns the AI needs to find.
How do they actually do that? Is it just looking at the squiggly lines over time?
Well, that's where one of the really key innovations highlighted in the sources comes in. They talk about creating 2D topographic brain maps.
Maps.
Yeah, think of it like this. You take the electrical activity measured by all the electrodes across the scalp at a specific moment or over a short time window, and you project it onto a 2D image, kind of like a heat map showing activity hotspots on the head.
Huh, interesting.
They also extract more traditional features, like looking at different frequency bands, alpha, beta, gamma waves, that sort of thing, and how they change over time. But this spatial mapping into a 2D image is a big deal.
So you're turning these complex electrical patterns across the scalp into something that looks, well, more like a picture. Why is that helpful?
That's the clever bit. It reframes the whole problem. By turning the EEG data into these 2D maps, they can suddenly use really powerful AI algorithms that were originally developed for computer vision for recognizing patterns in images.
Ah, like convolutional neural networks, CNNs.
Exactly. CNNs are incredibly good at finding spatial patterns in images, identifying edges, shapes, textures. And by feeding them these brain maps, researchers can leverage that power to find the subtle spatial and temporal patterns in brain activity related to speech.
Okay, so you're essentially giving the AI a kind of brain picture to analyze instead of just a stream of numbers. And the final output of this whole pipeline is the AI model input clean, structured data ready for the actual decoding.
Precisely. And then comes the AI model itself. That's the engine that actually tries to make the leap from these processed brain patterns to words or text.
And the sources suggest there's been quite an evolution in the types of AI being used for this.
Oh, definitely. The field has moved really fast.
Yeah.
It started maybe with simpler machine learning classifiers that could just distinguish between a few predefined thought patterns or words.
Okay.
But the clear trend, as shown in the sources, is towards much more complex deep learning architectures. Those CNNs we mentioned, or models like RNNs and transformers, that are specifically designed to handle sequences of data, which is obviously crucial for language.
And does all that extra complexity actually translate into better results? Better decoding?
According to the data presented in the sources, yes, absolutely. The trend they illustrate is pretty clear. As the models get more complex, and this is important, as they get trained on larger amounts of data,
Right, data is key.
their performance improves significantly. They become better at handling larger sets of possible words, larger vocabularies, and generating output that's more, coherent, more like actual language. These deeper models can automatically learn subtle, complex features from that noisy EEG data that simpler models might miss, and they're better at understanding the whole sequence, the flow of language.
Okay, so that naturally leads us to performance. What does the state of the art really look like today based on the benchmarks the sources provide? How good are these systems actually?
It's kind of a mixed picture. There were some really impressive breakthroughs, but also some very clear limitations still. The sources give a couple of key benchmarks to illustrate this.
Yeah.
One is a recent result from a model called D-Wave. It used non-invasive EEG to translate text that people were reading silently in their head.
Silently reading, okay.
And it achieved a BLEU-1 score around 40%.
40%. Now, for translation tasks, a BLEU score of 40, especially BLEU-1, which just looks at single words, it doesn't sound amazing, does it? Like, not fluent translation.
No, it's definitely not perfect fluent translation. You're right. BLEU-1 basically measures how many individual words in the AI's output match the original text. But what that 40% does show, and why it's significant, is progress in what they call open vocabulary generation.
Meaning, it wasn't just picking from a small list.
Exactly. The AI was attempting to generate text more freely, not just classify into a few known categories.
Yeah.
So while the accuracy number itself might seem modest compared to, say, machine translation between languages, achieving that level on this task from noisy EEG is actually a pretty big step forward in tackling the complexity.
Okay, so genuine progress on generating text from silent reading, even if it's, well, still a ways off perfection. What was the other main benchmark they mentioned?
The other one focused on imagined speech. So someone thinking about saying specific words but not actually moving their mouth or vocal cords.
Right.
And here, a different system achieved a much higher accuracy, 91.2% word recognition accuracy. This was specifically for decoding synthesized Chinese words from imagined speech, EEG.
Whoa, 91.2%. That sounds incredibly high.
It is very high, and it proves a really important point. The sources say it shows that intelligible audio can be generated from EEG. It demonstrates the potential to create audible speech just from thought, basically.
But there's a catch, I assume.
Well, the key difference is context. That 91.2% was achieved when recognizing words from a known limited set. It's really good at telling which of those specific Chinese words the person was thinking. But that's a different, arguably easier task than freely generating any word in response to spontaneous thought, like in a normal conversation.
And that difference seems to be exactly what the sources call the vocabulary challenge. It sounds like this is the major bottleneck for making this truly practical.
This is probably the biggest reality check presented in the sources, yeah. They show data, often in charts, demonstrating that while accuracy can be really high when the system only needs to tell apart a few words, say, distinguishing up from down or left from right, that accuracy drops dramatically as vocabulary size increases.
So the more possible words the AI has to choose from, the harder it gets and the more mistakes it makes.
Precisely. This fundamental limitation, which the data clearly shows, is what makes that dream of true conversational AI, decoding spontaneous, free-flowing, natural speech directly from brainwaves, such a difficult goal right now.
It makes intuitive sense.
Yeah. It's one thing to train a system to recognize, say, 10 specific command words with high accuracy in a controlled lab setting. That's achievable now. But it's a completely different ballgame to decode any word someone might think of, from the tens of thousands of words we use in everyday language in real time in any context. That's much, much harder.
So, okay, we've seen impressive progress, proofs of concept, high accuracy in limited scenarios. But decoding natural conversation is still a huge mountain to climb.
Absolutely. And the sources are quite clear about the major hurdles still remaining before we see practical brain-computer interfaces for communication being used widely outside of specialized research labs.
What are those key challenges they highlight?
Well, first there's the data bottleneck. We touched on this. But these complex, deep learning models, they are data hungry. They need massive amounts of high-quality, precisely labeled EEG data to train effectively.
And getting that data is hard.
Incredibly hard. You need reliable brain signals, accurately time-locked to specific words or thoughts. Collecting that from many people over long periods is really difficult, expensive, and time-consuming.
Just getting enough good brain training data is a fundamental issue.
It really is. Then there's the problem of generalizability. This is a big one. A model trained really well on one person's unique brain patterns often performs poorly on someone else.
Ah,
Sometimes it doesn't work at all.
right.
Or it might not even work reliably for the same person if you test them on a different day or if they're tired or stressed. Their brain state changes slightly.
So the models aren't robust.
They need to become much more robust, much more adaptable across different people in different conditions, different times, making the technology work reliably for anyone, anytime. That's a major challenge.
Makes sense. What else?
Hardware miniaturization. This is more on the practical engineering side, but it's crucial. For these systems to leave the lab and be usable in daily life, the hardware, the EEG caps, the amplifiers, the processors needs to get way smaller, more comfortable, less obtrusive than the bulky setups used in research today.
Yeah, you can't expect people to walk around wearing elaborate EEG helmets just to communicate.
Not realistically, no. And finally, perhaps the most profound challenge the sources raise: ethics and privacy.
Right. This must come up.
Absolutely. As this technology gets better, even approaching the ability to decode thoughts or intentions, well, it raises huge questions. Questions about consent, truly informed consent, about the security and ownership of incredibly sensitive brain data, the potential for misuse, surveillance manipulation. These are massive ethical considerations.
These aren't just technical problems, they're fundamental societal questions we need to grapple with as the tech develops.
Exactly. And the sources rightly highlight that these ethical frameworks and safeguards need to be developed right alongside the technology, not as an afterthought.
Okay, so wrapping this up, looking back over this deep dive through the sources, it feels like quite a journey. We started with that core challenge, finding the tiny speech signal amidst all the brain noise.
Mhm.
We walked through that essential, really complex processing pipeline needed just to clean the data up.
Yeah, turning raw waves into something usable.
We saw how AI, especially deep learning, has evolved to become the engine trying to make sense of it all.
Constantly getting more sophisticated.
Then we looked at the actual performance, those benchmarks showing, exciting potential, like that high accuracy on limited words, but also hitting that very real vocabulary wall.
Right, the gap between limited tasks and real conversation.
And finally, outlining those significant hurdles still ahead. The data problem, making it work for everyone, shrinking the hardware, and navigating those crucial ethical questions.
It really does paint a picture of a field with just incredible potential. The hope it offers for restoring communication for people who've lost their voice is profound.
Absolutely.
But it's also a field that, as these sources make very clear, requires a massive amount of continued scientific effort, engineering innovation, and very careful ethical thought.
It definitely gives you, the listener, a much more nuanced perspective, I think. You can appreciate the sheer cleverness of the breakthroughs that have been made,
Yep.
while also understanding the enormous scale of the challenges that still need to be overcome. It makes you think, doesn't it? Considering that vocabulary challenge specifically, what's the fundamental difference between decoding, say, 1 of 10 intended words versus capturing the sheer spontaneous complexity of how you think or talk every day? Is it just a matter of scale, or is it a different kind of problem altogether?
That's a really interesting question to ponder. And it ties back into those ethical concerns, too. As these technologies inch closer, even if full mind reading is distant, what does it mean for us, for society, when we start potentially accessing and decoding even fragments of that internal private monologue? It's definitely something to keep thinking about.